Right, so last time we were having a look at some of these examples and non-examples of norm spaces, Banach spaces, and so on. So let's get that out of the way. So R to the n and C to the n with those norm P's that we looked at were always complete, and it'll turn out that all finite dimensional norm spaces are complete, which we'll be proving in the near future. And if you use continuous real-valued functions or continuous complex-valued functions on, indeed, any compact Hausdorff space, you can put the uniform norm on it, and then it becomes complete. But if you put some other sort of weird norm on it, it usually isn't. And in particular, if you're working on the unit interval, if you use norm infinity, the uniform norm, then, so that uniform norm is norm infinity. The uniform norm is the one that gives you the notion of uniform convergence. And I'll be proving for you in a bit that you then get that with the uniform norm these spaces are complete. Well, I'll do one of them for you anyway. But not if you use the other ones. And we'll also have a look at that as well to see how do you show that one of these spaces isn't complete using one of these other norms. So what did we do last time? We had I reminded you about the norm, and what we looked at was uniform limits of continuous functions being continuous, and we proved that last time. So I asked you to revise uniform convergence and pointwise convergence. Has anybody had a look at that, and does anyone have any questions about uniform convergence and pointwise convergence for sequences of functions? If anybody has any questions about that, you can always contact me any other time anyway. But for now, I'm going to assume that you've revised uniform convergence and pointwise convergence. And you can always tell me another time that actually you're a bit confused about some of the details. So here you are, a sequence of continuous functions, real-valued functions I did on the unit interval, and I showed that if they converge uniformly to some other function, which is not at first assumed to be continuous or even bounded, so it's not immediately obvious that you can even use norm infinity in this situation. Nevertheless, the limit function does have to be continuous. So that was, we did a 3 epsilon over 3 proof to get our epsilon. So this is a typical thing. We said in order to show that f doesn't vary very much near a point x naught, the limit function doesn't vary very much near x naught, because nearby, one of the functions that's very close to it doesn't vary by more than epsilon over 3. And if that function that doesn't vary by more than epsilon over 3 is varying by less than epsilon over 3 nearby, then the epsilon over 3's combine, and the limit function can't vary by more than epsilon. And I invited you to have a think about that in terms of function balls and so on. So we've still got some more stuff to fill in before we move on here. I want to prove the completeness of the uniform norm on, say, we'll do it again on the continuous real-valued functions on the interval. And I want to check that some of the other ones aren't complete. So let's start by proving that the real-valued continuous functions defined on the unit interval 0, 1 with uniform norm is complete. In other words, it's a Banach space. You're allowed to say that the space, the norm space is complete, or you can say that the norm is complete. So you can have a complete norm, and you can have a complete normed space in which it's ambiguous whether it's a norm space that's complete or whether it's a space that has been complete normed. But in any case, that's a Banach space. And Banach spaces are what we're mostly interested in. So let's just check that the uniform norm works here. We have available the fact that a uniform limit of continuous functions is continuous. So what we're going to do is we're going to take a Cauchy sequence of continuous functions and prove that it converges uniformly to something. It will then follow that that thing it converges uniformly to is, in fact, continuous as well, and that the thing converges with respect to the uniform norm. So let Fn be a Cauchy sequence in this space. And I don't need to put the brackets around 0, 1. It's fairly standard that you can miss those out or put them in. It doesn't make any difference. Now, this is a 3-stage proof. But the second 2 stages can be done together. So stage 1, I'll do it as a 2-stage proof. The second stage really has 2 bits to it. So here's our strategy. Stage 1 will be to prove that Fn converges pointwise to some function f from 0, 1 to r, about which at first you know nothing. So you start by proving it converges pointwise to something. Pointwise convergence is pretty feeble. But because it's a Cauchy sequence, we'll then be able to do to stage 2 we'll prove that, in fact, Fn converges uniformly to this function f, and that f is therefore in CR of 0, 1, and that Fn tends to f with respect to norm infinity. So we'll do all the rest of it in one go. We prove that Fn tends to f uniformly on 0, 1. It then follows that f is continuous and once you've done that, we know uniform convergence is norm infinity convergence in that setting, and norm Fn minus f infinity tends to 0 and then tends to infinity. Okay, so that's our 2 stages. The first stage is relatively easy, using the completeness of the real line. The idea is that if you've got a Cauchy sequence of functions with a uniform norm, then whenever you look at the values it takes at a particular place, you get a Cauchy sequence of real numbers. So that's because when you're seeing how far apart the functions are, you take the supremum over all x in your space, in this case, closed interval 0, 1. So if you know that the functions are very close together throughout the space, it certainly shows that they're very close together at a particular point. So for stage 1 then, let's let I'll let A be 0, 1. Then for natural numbers m and n, you've got modulus of fm of A minus fn of A. Well, that's just one of the difference values. That's less than or equal to the supremum of all of those, which is the norm of fm minus fn infinity, which is the supremum over all values in 0, 1. what is a Cauchy sequence? Anyone remind me what a Cauchy sequence is? Okay, so the idea is that given some positive real number epsilon, if you go far enough down the sequence, there's some capital N, so that every pair of terms beyond that point is within epsilon of each other. So it's not just that successive terms are close together, but that all the late terms are near each other. So let me recall. This is not part of the proof, but I think it's worth recalling the definition of Cauchy sequence. Says here that for all epsilon greater than naught, there exists a natural number n such that for all m and n greater or equal to capital N, and it's understood that these are integers, we have norm fm minus fn infinity is smaller than epsilon. That's what it means for the functions to be Cauchy. I think with the real numbers is Cauchy if you have something similar but with just the modulus of the difference. So when you look at what's going on here, since the modulus of fm of a minus fn of a is dominated by this other value, norm of fm minus fn infinity, which we know is going to be less than epsilon if you go far enough down the sequence, it's now immediate. Going back to the proof, it's a sort of sandwich or dominated thing. If you've got a Cauchy sequence and you've got a whole load of values that come from it, and you've got some other sequence, you want to check it's Cauchy. If the differences are dominated by the other differences, then you know that this sequence is Cauchy as well. You can check the details of that. So it now follows immediately so since the sequence fn is Cauchy, that the sequence fn of a running from n equals 1 to infinity is a Cauchy sequence of real numbers. With, of course, the usual metric on the real numbers, which we know to be complete. If I don't tell you which metric I'm using on the real numbers, I'm using the usual metric. Okay? So that's the usual metric by default. So, by the completeness of R, this sequence converges in R. And we can define f of a equals the limit as n tends to infinity of fn of a, where a is any point of 0, 1. Notice we did that point by point. So at each point you get a convergent sequence. So this gives us pointwise convergence of the sequence of functions. Well, that's a good start. That's stage one. That was the easy bit. Any questions about this first bit? So why haven't we finished? Of course, I've told you what stage 2 is, but in general, if I get a sequence of continuous functions converging pointwise to some function, does the limit function have to be continuous? No, the limit function doesn't even have to be continuous. So we don't even know, it doesn't even have to be bounded, I don't think. So you could do pretty weird things. So we don't know very much about f yet, but we will do soon. What we've got so far is that f is a pointwise limit of the fn's. And now we go back to the Cauchiness and use it again. So for stage 2, we're going to prove uniform convergence and also get an estimate. We're going to get everything done at the same time. So let epsilon greater than naught. It's a Cauchy sequence, so we'll choose a capital N so that after a while all the terms are within epsilon over 2 of each other. That's just to be something less than epsilon, just to keep everybody happy. So since fn is Cauchy, there exists an n in N, so that this is a new capital N from before. For all m and n greater than capital N, we have the suit norm of fm minus fn. The infinity norm of that is less than epsilon over 2. Just to give myself a bit of extra room. If you do epsilon, what happens later is that something ends up less than or equal to epsilon. The problem with it, this is the problem with using strict inequalities and then taking limits, is that they can become non-strict. So I've gone for epsilon over 2 to make sure that I end up less than epsilon in the end. But if you're happy with less than or equal epsilons, then you don't have to bother with that. I'm going to claim that basically the function f is bounded and that the uniform norm of fn or fm minus f is less than or equal to epsilon over 2 once you get past n. So this n is going to be fixed for a while. Keep n fixed until further notice. And little n as well, and n greater with little n fixed. What do we have? We have, for all x in naught 1, let's call that star, modulus of fm of x minus fn of x is smaller than epsilon over 2 for all m greater or equal to n. Notice that I'm taking a particular n greater or equal to n for the moment. And I'm going to let m vary. Let m tend to infinity here. And what do I get?
Well, it goes past capital N at some point.
Okay.
Since capital N is
Yep.
constant, so
Okay.
necessarily needs to go past capital N.
Yeah.
N tends to infinity.
Okay, so we'll let m tend to infinity, and it goes past capital N, and so for all the later m's, this value is less than epsilon over 2. What happens to fm of x as m tends to infinity? It tends to f of x. And so you obtain modulus of f of x minus fn of x But do I know that it's less than epsilon over 2? We've got a sequence of values tending to this. Each of the values is strictly less than epsilon over 2. Well, at least once m gets past capital N. So what's the correct conclusion here? That it's less than or equal to epsilon over 2. Because a sequence of numbers less than epsilon over 2 could tend to epsilon over 2. So that's the worst case. Now, what is this valid for? This is valid for all x in 0, 1 and for all little n greater than capital N. For all x in 0, 1 and all n greater than capital N. By the way, you may wish to observe that this is less than epsilon. So what have I just proven? I took an arbitrary epsilon greater than 0 and I found a capital N so that beyond that point, mod fn of x is close to f of x within epsilon of x for all x in 0, 1. What does this prove? Okay, we sort of proved that, except that we didn't yet know that f was bounded. But somehow this actually does prove at the same time that f is bounded, and then you can do the suit norm. But on the other hand, since I only defined the suit norm really on the continuous functions, I should probably prove the function is continuous before I apply norm infinity. Or you can define norm infinity on the bounded functions. There's a choice of two strategies, okay? But any other comments? If you're not going to use the terminology of norm infinity, which you can fix that. Suppose you're not going to use norm infinity terminology. What other terminology could you use for what Fn is doing? We started with showing it was converged pointwise to f. That's right. We've now shown that Fn tends to f uniformly. For every epsilon greater than 0, we can do this, find this capital N, and after a while, once little n is bigger than capital N, yes?
Just do we use the fact that it is pointwise converged Fn to that?
Yes.
When going from that line to the other?
We only used it in going from this inequality to this inequality.
So we use pointwise.
That's where we use the pointwise convergence.
And why is it equal to it? Why can't it be sides?
Because a sequence of numbers that's strictly less than something can converge to the number. Just like a sequence of strictly positive real numbers can converge to 0. Like 1 over n is greater than 0, but 1 over n tends to 0. So suppose it was epsilon over 2 minus 1 over n, or epsilon over 2 minus 1 over m, would be less than epsilon over 2, but could converge to epsilon over 2. And that's the nuisance. When you're trying to get things to be less than epsilon, you always end up having to do stupid things with epsilon over 2s or something similar, just to make sure that you end up strictly less than epsilon at the end. Whereas if you rebrand everything and work with less than or equals throughout, then you don't have to bother with that. So that's the option. If you go back and look at the way I did uniform convergence for the second years, I used less or equals instead, simply because none of these problems turn up where you have to worry about the inequality changing.
By the way,
Yes?
is there a possibility to prove uniform convergence straight ahead and deduce the pointwise convergence on that?
Good question. I usually prove pointwise convergence first. I don't know how easy it is to prove uniform convergence directly, but I always think of this as a two-stager. Most of these proofs most of the proofs you'll see in this module are two stages. You first prove pointwise or coordinate-wise or something convergence, and then you come back again and substitute it back in. It is a very common proof structure. If you can find a direct proof, I'll be interested to see what you come up with. Okay, so we've now shown, this shows that Fn tends to F uniformly on 0, 1. From which you conclude that shows that F is continuous, because we know a uniform limit of continuous functions is continuous. And now you're allowed to use norm infinity and say that that's the same as uniform convergence. So since norm infinity convergence is uniform convergence, Fn tends to F in this space, CR01 with norm infinity. And we finished.